Uh, Today I will talk about challenges faced in modeling fusion applications and give a short introduction to the Thinshell method we have implemented in AllSolve. And the goals of the presentation is to highlight the challenges and the origin of those, give the background to the Thinshell method, and demonstrate the benefits of the Thinshell method over the volume-based modeling. And also I want to show how does the Thinshell conductivity affect the ramp-up dynamics of a partially insulated coil. So, origin of challenges. You are very well aware of this. So, they are typically the high aspect ratio and the large and complex geometries, especially in fusion field. Here we have a couple of examples. The other one is a Viper cable example. You can see that there are HTS stacks embedded in conducting materials, and the cable is twisted itself. And typically the superconducting tapes can be, the dimensions are less than 1 millimeter, and then the aspect ratio, if we would take the individual tapes into account, it's huge compared to the cable itself. And easily, if we want to increase the details to the geometry, we will end up having huge problems to simulate. And typically, it's not even possible, and we need to do some homogenization there for the tapes or the stack level even. Then here's another example of a stellarator geometry. This is a project by Proxima Fusion, and in this case you can see the aspect ratio as well. We are talking about several meter diameter of a magnet, and then the cable, the superconducting stack itself is around 12 millimeter. And even though it would be homogenized, the problem becomes really big easily due to the complex material layers around the cable. Also, the geometry is very complex, and there's no way we can exploit symmetry there, so everything needs to be done in 3D, and the problem becomes easily very big. And before I go any further, I really would like to thank Proxima Fusion and Athlete Engineering for this really interesting collaboration project and opportunity to participate that. Then, what can we help to improve the accuracy of the models? And the possibility to take into account more details in the model. One option can be Thinshell method. And 2022, here on the right, we can see the basic idea of the Thinshell method. It was introduced by Alves et al. At Montreal, and there's the general idea behind is that we can, in 3D, we can present thin volumes as surfaces, or in 2D, we can represent surfaces as lines, and this will reduce the complexity of the geometry and CAD, as well the meshing significantly. And the method behind is to introduce a virtual finite element problem for the Thinshell domain only. And fields inside the thin cell, they are approximated using linear basis functions. So on top of H5 formulation, we can introduce a new thin cell formulation for the thin surfaces. So what we have done is we did simulation to compare the thin cell method against the volume-based simulations. And you can see the geometry here on the right. The blue one is a cable spiraling around, and it has a thin volume layer around it, and everything is embedded in steel structure. Here on the very right, you can see the very thin conducting layer around the cable. And this is everything is meshed in the volume-based approach, and in the thin cell approach, we neglect the green area, so it doesn't exist in the model nor in the mesh. And here's the result on the left regarding the mesh. You can see that for the volume-based approach, where we really have the actual volume present, we need to do very fine mesh also in the cable in order to have a decent mesh in the thin layer. Whereas when using thin cell method, we don't need this additional thin layer at all in the model, so we don't need to refine the mesh in the cable so much, and we can easily reduce the size of the problem. For example, in this case, with this mesh we had 5.6 million elements in the volume-based mesh, and for the thin cell mesh only 0.59 million elements. And when solving the problem, it resulted in 0.7 million unknowns for the thin cell method, whereas we had 5.5 million unknowns for the volume-based approach. Here are some details. Cable was 6 times 6 millimeter, and the thin layer was 0.1 millimeter thick. And in this case, the mesh with respect to the domains on both sides of the thin cell, it was conformal, so they shared the same nodes. Some results. We did 3 different simulations. Simulation cases, and in the first one, the conductivity for the thin cell was very high. We wanted to see that the current is flowing in the thin cell and to compare the net currents between the different models. So in this case, we had the cable conductivity the same as in steel. And on the leftmost figure, you can see the magnet field dynamics during ramp up. So the red curve is always the applied current, and we can see that there's a delay in the magnet field rise up. Then we have the losses and the net currents in different turns. At the very top turn and in the middle turn. You can see that the models are matching pretty well. There's only 5% difference in the losses and less in the other quantities. Uh, then second case, we introduced a poor conducting material for the Thinshell, and also the volume, of course, for the thin volume. And here are the results for that. They are almost in perfect match in this case. So the field is rising in the same rate as in the both models. Also the losses are the same. However, you can see differences now in the net currents. However, if you compare the amplitude of the current, it's negligible to the applied current. So this basically noise level signal in the Thinshell, and this can be really affected as well by the mesh. So the mesh is not that accurate in the Thinshell model anymore, since we are using bigger elements there. Case 3, we increased the conductivity of the Thinshell. So now there's more a better path to bypass the cable in this case. And from compared to the last one, you can see that already the ramp up time is higher here. Before it was 30 seconds. Now it takes 50 seconds to achieve the stable conditions for the magnetic field. And again, you can see pretty nice match with the two models. And here, now in this case, the losses are a bit different. But now the losses are negligible to the losses in the cable and steel again. And they are almost negligible in the model. So as conclusion, the Thinshell method agrees very well in this linear comparison we made against the reference simulations with volume-based model. In these cases where the investigated quantity was almost negligible, then the correspondence between the models was not that good. If we compare the simulation times, for example, in this 50-second case, it took about 2000 seconds and for 26 nodes for running the volume-based model, and half of that for the Thinshell simulation with only one node. So here you can see already a big difference in simulation time, and you can save many core hours as well using the Thinshell method here. Finally, before going to the demonstration, here are the field plots for the current distribution in red here, the red arrows, and also on the slices you can see the magnetic field distribution. And this is the second case we studied, and you can see that also visually there's a nice match between the two methods.